Picture the nuclear control room you've seen in movies. Flashing red lights, alarms screaming from every direction, operators sprinting between consoles, pulling levers, shouting readings across the room while a digital countdown ticks toward disaster. Now forget all of it. The real thing looks nothing like that. The first time most people see an actual nuclear power plant control room, the reaction is almost always the same. It's quieter than expected. The lighting is flat and fluorescent. Two operators are sitting at a long console, watching screens, occasionally making notes. Someone has left a coffee cup on the desk. There is no drama. There is no tension visible on anyone's face. And this is not because nothing important is happening. It is because everything is working exactly as it should. Today we're going inside the real nuclear control room. And by the end you'll understand why the most dangerous moment in a nuclear plant has nothing to do with alarms. It's the 15 minutes when one crew hands control to another, and everyone in the room already knows exactly what they're doing. Let's start with what the room actually looks like, because the physical environment tells you everything about the philosophy behind it. A modern nuclear control room is typically a large rectangular space, maybe the size of a school gymnasium, with very low ambient noise and carefully controlled lighting. The walls are lined with instrument panels, status boards, and display screens showing real-time data from hundreds of sensors distributed throughout the plant. The main operator console sits at the center, a curved or linear workstation where two licensed reactor operators sit during every moment the plant is running. Behind them, a shift supervisor monitors the overall picture from a slightly elevated position. The room is designed to be calm, not comfortable in a relaxed sense, but calm in a controlled sense. Everything is labeled. Everything has a designated place. The color coding on switches and indicators follows strict conventions so that any trained operator, even one who has never worked at this specific plant, can orient themselves within minutes. This is not an accident. It is the result of decades of human factors engineering, the scientific study of how people interact with complex systems under stress. The physical design of a nuclear control room has changed dramatically across generations of plants. And those changes tell the story of everything the industry learned the hard way. Plants built in the 1960s and early 1970s were designed by engineers who prioritized completeness over clarity. Every system had its own dedicated panel, its own set of meters, its own bank of switches. The result was control rooms that wrapped around operators in a full semicircle of instrumentation, hundreds of square meters of dials and indicators, where the sheer density of information was itself a source of risk. A trained operator in that environment knew where everything was, but only because they had spent years memorizing a layout that had no organizing logic beyond the order in which the systems were installed. When something unusual happened, they had to mentally navigate that memorized map under stress, searching for the right indicator among hundreds of similar ones. Later generations of plants introduced more systematic organization, grouping related systems together, using consistent visual hierarchies, and reducing the number of controls that an operator needed to interact with during normal operations. The most modern digital control rooms, built or refurbished in the last 20 years, present operators with a computer-driven overview display that shows the entire plant status in a single integrated picture, with the ability to drill into any system with a few keystrokes. The change from the first generation to the latest is not just aesthetic. It represents a fundamental shift in the philosophy of what a control room is for, not a place where operators control a reactor, but a place where operators understand one. What strikes visitors most is how little appears to be happening on a normal day. And that is precisely the point. A nuclear power plant running correctly is one of the most boring workplaces on Earth by design. The operator's primary job during normal operations is not to control the reactor. The reactor controls itself through passive physics. Their job is to monitor, to watch thousands of data points flowing across their screens and notice when something deviates, even slightly, from where it should be. A temperature reading that is 2 degrees higher than the trend line. A pump vibration sensor showing a frequency shift that is within tolerance but different from yesterday. A valve position indicator that matches its commanded state but has taken half a second longer than usual to respond. None of these things are alarms. None of them require immediate action, but a trained operator notices them, logs them, and flags them for the maintenance team, because in a nuclear plant, small deviations caught early are the entire system working as intended. The instruments themselves deserve a moment, because the sheer density of information in a nuclear control room is unlike almost any other working environment on Earth. A typical large pressurized water reactor has somewhere between 30,000 and 50,000 individual sensors monitoring every aspect of the plant's operation. Coolant temperature and pressure at dozens of points throughout the primary and secondary loops. Neutron flux levels in the reactor core. Steam generator levels. Turbine speed and output. Radiation monitors at dozens of locations inside and outside the building. The status of hundreds of valves, pumps, fans, and circuit breakers. Not all of this data flows directly to the control room in raw form. It is filtered, prioritized, and organized into a hierarchy of displays that presents operators with a manageable picture of the plant's overall status, while still giving them the ability to drill down into any individual system in seconds. Have you ever wondered what it takes to hold the entire state of a nuclear power plant in your head simultaneously? The answer is that no single person does. The system is designed so that the picture is always in front of you, updated in real time, demanding nothing more than your attention and your judgment. The shift handover is the moment that nuclear safety experts point to most often when they discuss operational risk, and it is worth understanding why. Every 6 to 12 hours, depending on the plant and the country, one crew of operators leaves the control room and another takes over. This transition takes approximately 15 minutes. During those 15 minutes, the incoming operator must absorb the complete current state of the plant, every ongoing maintenance activity, every system that is in an unusual configuration, every trend that the outgoing operator has been watching, every standing order or temporary procedure currently in effect. The outgoing operator must communicate all of this clearly, accurately, and completely, while also being tired from the end of their shift and ready to go home. Studies of nuclear plant incidents consistently show that a disproportionate number of problems begin in the hours immediately following a shift handover, when the incoming crew is still building their mental model of the plant state, and is most likely to misinterpret an unusual reading or miss a subtle trend that the previous crew had been tracking. Modern handover procedures are extraordinarily detailed precisely because of this risk. Written logs, formal verbal briefings, mandatory checklists, and in some plants, recorded audio of the handover itself, all designed to close the gap between what one crew knows and what the next crew needs to know. But what actually happens when something does go wrong? On the morning of March 28, 1979, operators at the 3 Mile Island nuclear plant in Pennsylvania encountered a situation that the training system had not prepared them for in the way it needed to. A small equipment failure triggered a chain of automated safety responses that were all working correctly, but whose combined effect created a plant state that was genuinely ambiguous. The operators, trained to respond to the most likely explanation for what they were seeing, made a series of decisions that seemed logical given their understanding of the situation, but were based on a misread of a key indicator. A relief valve had stuck open, slowly draining coolant from the reactor core, but an indicator light in the control room showed the valve's commanded position, not its actual position. The operators believed the valve was closed. They were wrong. Over the following hours, a combination of human decision-making errors and instrument ambiguities allowed the situation to develop in ways that were more serious than anyone in the control room initially understood. No one died. The containment structure held. But the event exposed a fundamental gap between how control rooms had been designed and how human beings actually process information under stress and uncertainty. The contrast with Chernobyl 7 years later is instructive because the two accidents failed in completely different ways. At 3 Mile Island, the operators were trying to solve a problem they had misdiagnosed. At Chernobyl, the operators were following a test procedure that had been designed with inadequate understanding of the reactor's behavior at low power, and when the reactor began behaving unexpectedly, the procedures they had been given left them without a clear path to safety. In both cases, the control room itself, the physical space, the instruments, the procedures, was a central part of the failure. Not because the technology was wrong, but because the system as a whole, including the operators, the procedures, and the instrumentation, had not been designed to handle the specific situation that developed. This is the lesson that reshaped the entire industry. A nuclear control room is not just a collection of instruments and switches. It is a socio-technical system, one where the design of the room, the training of the operators, the quality of the procedures, and the culture of the organization are all equally critical components of safety. The lessons from 3 Mile Island and Chernobyl rebuilt the entire field of nuclear control room designed from the ground up. Human factors engineering became a central discipline rather than an afterthought. Control rooms were redesigned to reduce ambiguity, to make the actual state of every system unambiguous rather than inferred. Alarm management was completely rethought. Before TMI, a nuclear plant alarm system might activate hundreds of alarms simultaneously during a developing incident, overwhelming operators with noise at precisely the moment when they needed clarity. Modern alarm management systems prioritize, filter, and sequence alarms so that operators receive actionable information in a manageable flow rather than an undifferentiated flood. Simulator training was dramatically expanded so that operators now spend hundreds of hours every year in full-scale replica control rooms working through scenarios that the real plant may never experience, building the pattern recognition and procedural fluency that allows them to respond correctly under pressure. And this brings us back to the coffee cup on the desk. The operator drinking coffee in a quiet control room is not being careless. They are the product of a training and certification system that is among the most rigorous in any civilian profession. In the United States, a licensed reactor operator must pass a written examination, a comprehensive simulator examination, and an annual requalification process that includes regular evaluated simulator scenarios. The boredom is not complacency. It is competence. The quiet is not emptiness. It is a room full of people who have internalized the state of a 50,000 sensor system so deeply that nothing about it surprises them, and who are trained to treat any surprise, however small, as the beginning of something that deserves their complete attention. The nuclear control room is one of the few places on Earth where being unremarkable on any given day is the highest possible standard of achievement. And here is what that means the next time you read a headline about nuclear energy. The danger was never the dramatic explosion of a movie meltdown. It was always the quiet accumulation of small misunderstandings in a room that looks nothing like what you imagined, managed by people trained to be the least dramatic professionals in the world. If you want more deep dives into the hidden systems and the people who keep the most extreme places on Earth running, subscribe. What's coming next will be even more interesting.